Okay, so allow me to introduce today's speaker, Dr. Tao Yang from Technical University of Munich. Um, he's a postdoctoral researcher working in Stefan Marber's group. And today his talk will be on the application of fibers and textiles for acoustics. Yeah, floor is yours, Tao. You may share your screen.
Thanks a lot for Sebastian and Ken's invitation. We met first time during the Sydney Acoustic Conference in last December, right? December or November, December. But the conference schedule was really tight, so I wasn't able to find the time to visit CAAV. That's a pity, but anyway, today is a good time to present my work and to see is there any collaborations potential between you group and me and my other colleagues. So I came to Europe, the Czech Republic, in 2015 to start my PhD study, and then I spent 5 years on PhD. After defense, I started to work there for 3 more years, and to 2021, I applied for the Mercury postdoctoral fellowship. Fortunately, I got the fellowship on second year. Then I joined Stefan Marber's group on the end of 2022. Because since I start my I worked on fiber materials acoustic properties from my PhD study, so my research topic more related to acoustic, thermal, and air penetrating behavior of fiber material. But today I only talk about the acoustics. So I will introduce about the acoustic comfort and tell a little bit about the background. And then I spend more time on sound absorption, then sound insulation and optimization. The optimization is for sound absorption, but with either thinner structure, means less thickness or less weight. Afterwards, I will give a very short talk about the smart textile. The last point is about the outlook for fiber and the textile for acoustics. So maybe in this session, we can see is there any point to collaborate. I guess you and your teams have the background about acoustics, so you already know such kind of lactic effect about noise pollution to our health, to our body. And I guess almost everyone either suffered or currently suffering for the noise. I checked on the internet. There is a quite striking statistics concerning the dangers of noise pollution in Europe. So it was released by the European Environment Agency. They mentioned that there are 12,000 premature deaths because of the noise pollution, and every year there are around 50,000 new cases of heart diseases. So it's quite serious in Europe. I think it's more serious than in other countries, for example, China or India. So the primary purpose for noise treatment is to reduce the lactic effect from the noise pollution. But as our demand increase, we need not only less noise, but also an environment with acoustic comfort. It's necessary to briefly introduce the difference between sound absorption and sound insulation. In the sound absorption, we usually use porous material to absorb sound energy to reduce noise and to prevent them reflect to the space. Sound insulation is the process to prevent sound from passing through a material. Solid or thick structure are mainly applied to insulate the soils, but these two methods they always apply together in practical applications. I think in some papers or publication, people still confusing about the sound absorption mechanism. It's mainly due to the viscous thermal effect. And the viscous effect is the friction between the air and the like pore walls or fiber walls due to the air viscosity. And the thermal conduction is the thermal energy transfer between air and the absorber. In these two effects, the viscous effect is the dominant one. In most cases, I think the viscous effect is contribute more than 90 or 80% sound absorption. If we talk about the textile for sound absorption, we can take like different structures. For example, generally textile can be categorized as woven fabric, knitted fabric, and non-woven fabric. But because woven fabric is always very thin, so it has very poor sound absorption. So it doesn't use too much for sound absorption. For the knitted fabric, there's a kind of special technology. They can generate very thick structure. For example, this fabric called space fabric. It can reach 20, 30, even 40 millimeter thickness. And then it achieve kind of good sound absorption compared to the woven fabric. Actually, compared to the knitted and the woven fabrics, the non-woven material is dominant in the market so far. I think you may remember if you've been to the exhibition during the acoustic Sydney, there's plenty of manufacturers that are still developing porous or fibrous sound absorber. I think that's still the main market in sound insulation and sound treatment for room acoustics. It's just because non-woven fabric they are usually have good sound absorption and lightweight, cost effective, easy to install. And you can see if you can design the material in a good way or produce in a good way, they usually have good sound absorption. Then turn to the fiber types. In general, we can sort the fiber as natural fiber and synthetic fibers. The conventional sound absorber, for example, glass fibers, they are in the category of synthetic fiber. But nowadays, I can see people are trying to use natural fibers to replace such kind of synthetic fibers. In one of my review paper, I compared plenty of the natural fibers with the conventional glass fibers. In the left graph, it shows the comparison between natural fiber and the glass fiber with a 30 millimeter thickness. We can see plenty of the natural fibers have like superior sound absorption. For example, caleb fiber, pineapple leaf fibers. Then in another group is the fibers is a sound absorber have the thickness over than 30 millimeter. Also the pineapple fibers exhibit very good sound absorption than the glass fiber. It might be not very clear from your side, so if you need to get more data or if you are interested, just write me. I can share the whole point. So in the real application, there are different ways to form the sound absorber. The first one is quite interesting, called greenery wall. I think it was commonly used in Singapore. So in Singapore, they have a lot of like a vertical greenery wall. It's very good for the environment, and the second, it can also absorb the sound and somehow deal with the noise pollution. Then the second group is the fiber assembly, which is mostly used in current applications. And then the last one is the fiber composite. is still a porous material. It can let sound penetrated, but it has enough mechanical properties in some cases. Last year, I presented a work regarding the most critical factors for sound absorption. Because I worked on this topic for years, and it's necessary to figure out the most important critical factors. And if we could have a simple criteria to evaluate the sound absorption of fibers, it would be very great. And I made a quick search on Scoop, put the acoustics and keywords as acoustic sound absorption or transmission loss, and microstructure structure parameters to see how many papers have been published per year. So it was keep increasing the publication amount. But so it means people are still trying to figure out the most important parameters or factors for sound absorption. So generally, plenty of micro and macro characteristics have influence on the final macro properties, such as thermal insulation, sound absorption, sound transmission loss, and the fiber diameter, pore size, porosity, and tortuosity are typical micro characteristics. Airflow, resistivity, density, thickness, and so on belong to the macro characteristics. And all of these microstructure and macrostructure together affect the final macro properties. In my point of view, the most important factor is the thickness, because there's a quarter wavelength resonance. If we increase the thickness, we can significantly improve on sound absorption. And the perfect or highest sound absorption shift to low frequencies, because most time we got a problem for sound noise, the noise in low frequency range, for example, below 1000. And the next factor is the fiber orientation. So in these two geometry, you can see the sound wave is perpendicular to the fiber direction orientation. But another one, the sound wave, they are aligned, they are perpendicular or parallel, parallel to the fiber direction. The first one, obviously, it has a much bigger tortuosity, so the sound wave get inside to penetrate in the randomly collected pores. But for the aligned fibrous media, the sound wave just goes through the media. There's no such randomly or complicated pore connection. And then they showed a very big difference on the sound absorption. In my opinion, the last most important factor is the surface area. As I mentioned, the sound absorption is because of the viscous thermal effect. So if we have a large surface area, it means more viscous effect and more thermal transfer involved. And here is the JCA model, numerical modeling. And I changed the parameter of viscous characteristic length, which is related to the surface area. Lower viscous characteristic length means higher surface area. So if we lower the value from around 1000 to around 10 or 5, so we can see the best sound absorption shifting to low frequencies. That's what we want to see. But most of the models or the studies, they usually ignore the fiber contact. So the fiber contact omitted. So then the surface area are usually overestimated. That's why in most cases, when the models can't accurately predict the sound absorption, is because they ignored the fiber contact. For example, the JCA or JCAL model. Here's the example of fiber contact. For example, in the image A, there's a true twisted yarn, and the image B, that's a so-called false twist yarn. You can see because the fiber contact in the true twist yarn is much more than the false twist yarn. So definitely, in the yarns in the image B has much bigger surface area than the true twist yarn. Here's two examples to see how surface area affect the sound absorption. In this image, the fiber diameter is around 3 to 4 micrometer. On the another one, the fiber diameter is around 20 micrometer, but they have the same thickness. And if the fiber is more thin or smaller, it always means it has a larger surface area. So the black one represents the sound absorption of the fiber diameter around 3 to 4 micrometer. Then the right one is the blue line, so you can see it has much better than the regular fibers. If we talk about the sound insulation, there are 3 types of fibers in one paper they presented. So one is round fiber, the second one is called octolobal fiber, and then the last one is trilobal fiber. I think it's easy to understand that the middle one, which is octolobal fiber, has much bigger surface area than the regular round fiber and the trilobal fiber. So you can see here the octolobal fiber, it has like a better sound insulation or sound transition loss than the other 2 or 3 types. So actually, below, I have talked about the sound absorption, and then here is about the sound insulation. Actually, I didn't do too much work on sound insulation, so I just introduced the real applications for the sound insulation. For example, in the automobiles and aircraft, they often use various sound insulation solutions to reduce the noise level and improve acoustic comfort. The common methods for sound insulation is including using sound absorbing material in engineering compartment, adding sound barrier to the wheel wells and underbody, and install acoustic laminates in the cabin. Here I like to introduce something I currently working on. So it's about the optimization, but it's not about the metal material or the metal structure. In my work, I try to reach the sound of the best or the optimized sound absorption, but with either less thinner structure or less weight material. Why? Because although we can reach the nearly perfect sound absorption after 500 hertz with I can say very good design metal material, but in this metal material they are using 4 units to combine one sound absorber, and in each unit there are 16 different fabric parallel resonator. On end, they added one 3 mm layer of sponge, then to generate such great sound absorption. But the thickness of the sound absorber is more than 10 centimeter. I think it's quite large, and also the design is, in my opinion, is quite complex. So my idea to use a simple material, simple structure to achieve comparable sound absorption. I presented part of this work in acoustic signaling. So the motivation is to optimize sound absorption of fiber material, and of course, it should be able to determine the structure parameters and then to use the structure parameter to design the sample, the specimen, to carry out the measurement. Because the Johnson sample large model is more robust compared to the other empirical model, for example, Mickey model. But it has too many non-acoustic parameters. And in my current work, I use the multi-layer structure. So in the multi-layer structure, the porous layer and the air layer, they are alternatively arranged. It means the sound wave come to the top, and the first layer is porous layer, second layer is air layer, and it's continually repeated. Why I say it can be the preliminary work on design of adjustable multi-layer sound absorber, because I hope I could develop some structure. For example, the single layer can be splitted as 2 layers or even more, and these 2 layers can be moved or adjusted along the sound wave direction to have a tailored or desired sound absorption in some certain frequency range. Before conducting the optimization, we should have a target sound absorption. So first, I choose the first target sound absorption when the perfect sound absorption reached and 1000 Hertz. And then because usually perfect sound absorption is happened when the quarter wavelength resonance is around the characteristic by Beard frequency and the high porous media. So that's a Beard frequency and 1000. Then we can calculate. We set the F0 as 1000. Then we set the porosity as 98%. Then we can have the tortuosity by this empirical model. Then we can have the airflow resistivity. With the airflow resistivity and the thickness, we can easily get the target sound absorption by the Mickey model, because in the Mickey model, we only need the thickness and the airflow resistivity. So that's the target sound absorption we need for the first target. It's quite interesting. We found when I plot the graph, the nearly perfect sound absorption happened like around 850 instead of 1000. It means in some cases, if the material is thick enough, it's no longer 1/4 wavelength resonance, but a little bit smaller. But it didn't work for material like lower than 40 millimeter. That's another target. So the high we set the highest find the highest sound absorption before 3000 Hertz for various thickness. For example, from 30 millimeter, 40 millimeter to 80 millimeter. Same as the previous slide, we calculated the airflow resistivity and get the tortuosity, and also use the Mickey model to plot the target sound absorption and also the normalized surface impedance. Then I use the least square method to find the minimum value of this function to get the most close curves on the normalized surface impedance. In this equation or function, I need to calculate the minimum value, this part, and also the imagined part of normalized surface impedance, and then get the minimum value by the ladder mat algorithm. But usually, if we use the original JCAL model to do optimization, it's possible. And all the results of the non-acoustic parameter we achieved here is in a reasonable range. So this is I don't know you're familiar with JCAL model or not, but just to briefly introduce this model is quite robust and it contains 6 parameters. Then in the optimization, we can get the thickness, porosity, airflow, resistivity, tortuosity, viscous critical length, thermal critical length. Last one is static thermal permeability. But okay, we got such long acoustic parameters. The point is, how can we produce the material with such exactly the same parameter? In my opinion, is impossible to prepare or produce exactly the same material with such parameters. So then what idea came to my mind. I simplified the JCAL model from 6 parameters to 1 parameters to 1 parameter. For example, it was required airflow, resistivity, and so on. And then on the end, I only use the porosity to predict the surface impedance and some absorption of the porous material. Is because if we use the same fibers, you can see here the empirical models or theoretical models for such long acoustic parameters. All of them are related to the porosity and the fiber diameter, actually the fiber diameter. And then we can simply, if the material is the same, so we can consider the rest part of the porosity as constant. So I set them as the constant for different long acoustic meters from A, B, C to E. Then I measured measurements for different porosity material, and then get their long acoustic parameters, and then use a simple regression method to plot their relationship between porosity and such long acoustic parameters. Then I validated the simplified JCAL model. It looks quite okay, and for porosity from 92 to 97, the simplified model is quite accurate. But I didn't put the graph here, but we got a problem for the high porous material, which is 99% porosity. The both original and simplified JCAL model can't predict the sound absorption, the sound absorption and the surface impedance in a good agreement. So I'm still trying to figure out the reason for this. I guess it might because of the elastic movement, because it's the quite high porous, the fibers may start to move. So that's why it happened. But we need to do further investigation. As I mentioned, because we could reach comparable or still the great sound absorption, and then I use a multi-layer structure, so we can somehow lower the weight of the material, because it's not really possible to decrease the thickness if we are only using very simple porous material or fiber material. But then I use a multi-layer structure to still reach a good sound absorption, but there has very good weight reduction. For example, this one, the maximum weight reduction is around 31%. And then for the even layer structure, for example, 2 or 4 layers, they have higher weight reduction because the even layer structure has one more layer of air compared to the all layer structure. So that's why it has a better, higher weight reduction. In the smart textiles, so far I only know there's one type of smart textile, smart fabric for acoustics. So this work was published on either Nature or Science, I can't remember. They developed the shirt with a piezoelectric sensor or ions inside. So this shirt is able to record the sound and then convert it to electrical signal, and then can be spit out or played out from some speakers. It's a video. I don't know. It's good to play it. Maybe someone interested in, I can show him the slides of the video. The last section about the outlook. So during my research period, I investigated the effect of structural parameters on sound absorption. I applied some impedance models on fiber material, and I did a work with Korea Hosenko from Sheffield University in the UK on the accuracy of airflow related models for fiber material. Then I applied the acoustical inverse characterization on textiles and fibers. I did some investigation for natural fibers. And then last year, I investigated the most influential factor for sound absorption. The red arrows means the current project I'm running on. So the first one is I just presented the optimization of sound absorption of fiber material. And actually, I applied the medical product fellowship with the topic of textile-based material. So this project is currently running. And I hope in this section we can find some collaborations to see is any like mature interest we can work out together. This research work I did in the first 2 years of my PhD study. So I investigated the different spectrometers effect on the sound absorption. Some interesting findings was discovered. For example, for the fiber material, if the porosity around 90.5 to 98, usually has the best sound absorption. And for the airflow resistivity, if it is value in the range of 5K to 7K, the sound absorption is always better than others. Here is the application of different impedance models on fiber material. So I used the dynamic Bentley model, Mickey model, and the Garai model. The last one is called Komatsu model. Of course, I also applied the JCA and JCAL model on fiber material. Some of them are quite good and accurate, but not all of them. I did this work of acoustic inversion for textiles with Yanfinish in France. So I investigate plenty of fibers to use the impedance dual measurement and inverse characterization to figure out some parameters that really hard to be measured in practical methods. For example, the correct weakness and thermal permeability. And that's some work related to the acoustic properties of natural fibers, for example, the wool fiber and the cotton fiber. And that's the point I mentioned on the beginning of optimization session. So if we could have the adjustable or movable layer of porous material or porous layer, we could reach very good sound absorption in such broadband frequency range. So of course, if we can make it activity, we can just reach any frequency, any sound absorption in any frequency range we need. If we could split one layer to two layers and also make them freely movable along the sound wave direction, then we can even reach the perfect sound absorption in the almost the whole frequency range from 700 or 800. I'm trying to figure out how to make them movable or adjustable. I think we currently have a clue on it. The point is how to manufacture or produce such device or specimen to make them adjustable. I think Ken is working on metal material, so maybe he's quite familiar with this video. Because the textile structure or the textile material, they are soft and flexible. My idea for the Mercury postdoc fellowship was supposed to develop a textile-based metal material, but it's still running now. For example, this tube is made by 3D weaving technology, and it means that this is just too simple structure. It means if you could develop more complicated structure, definitely we could achieve flexible and tunable and adjustable metal material by textile fabric. Yes, I think that's my presentation. Thank you for your attention. If you have any question, please feel free to ask me.
Yeah, thank you, Tao. I think that was a very interesting and very comprehensive presentation. I open the discussion, and if you have any questions, Tao, please feel free to ask him. Yeah. Okay. Sebastian, I think has a question. Yeah.
Hi. Yeah, thanks. It was a very interesting presentation indeed. Can you go to, I think it was slide 19.
19, okay.
19, yeah.
Yes, here, yes.
No, where you had the bar diagram, where you had the different different layers, 2 layers, 4 layers.
Okay, here.
No, the bar diagram with the thicknesses on the x-axis, and then the different 2 layer up to 4 layers. Maybe 29? Yeah, this one. This one, 29.
This one, okay. Oh, sorry.
29.
This one, yes.
Sorry, yeah.
Yeah.
Yeah, okay. So for 2 layers and 4 layers, we kind of see a trend, right? And then but then the 4 layers overtake the 2 layers. But for the 5 layers, why is it so different between 5 and 3 layers?
Yes, it's well, I think it's hard to say it's kind of a trend because there are different thickness, so they are kind of independent. But it's just from the results of optimization. So I think for me it's hard to say why the trend is like that because all of the data is from optimization.
That's what I mean. It's just optimization, and so you have a linear increase in thickness, and you have always the same configuration. I'm just wondering. So for 2 and 4 layers, I see a pattern, right? For the others, not really. So So especially 70 millimeters. Why is the 5 layers so much higher? So something is interesting to explore this. I mean, yeah.
Yes, good point. Yes. Yes, actually, I did the automation just last week, so I didn't run the measurements yet. So today I will run measurements.
Okay.
I will see
Okay. Yeah.
whether it's same as I expected. So and I think I missed some points because for we could simplify the JCL model and with one parameter which is porosity, and then for me it's very easy to prepare the specimen, and then I just need to measure the weight of fibers and then put them in the pitching tube to the measurement. So these are just based on the simplified JCL model. So maybe today after the meeting, the seminar, I just go to lab to check whether they are the similar as the optimization result. Thank you for the point.
Is there any other question from the audience? Okay, maybe I ask one question. So
yeah,
I suppose you were using the impedance tube model for these optimization studies, right?
Yes,
I wonder
yes.
if you also did any dimensional studies, like for a larger textile object versus a smaller sample. How does the absorption coefficient change with respect to dimensions?
The dimension of what? Of the material or specimen?
Specimen, yeah.
Well, since we have one impedance tube in our lab, mostly I use the impedance tube to carry out the measurements, and of course the specimen is quite small, so and I only use a small tube with a 40 millimeter inner diameter, and so far we didn't carry out any kind of large scale measurement for the large sample in the revelation zone. So I have no idea. Is there any difference between like a small scale or large scale sample? But I heard that if because in the reverberation chamber, not reverberation chamber, the such kind of chamber, we place at least 6 square meter specimen in it, and then to see the sound observing difference. And it's more for random incidence sound wave, but for the impedance tube measurement is for normal incidence. So for sure, if we do large scale measurement, the sound observation will be a little bit higher or better than the result we get from the impedance tube. I hope I answered your question.
Yeah, thank you for the answer. I think Abhishek has a question.
Yeah. Hi. Yeah. Nice talk. Nice presentation. So, my question is related to somewhat in this, like what you have shown. So, when you design all these different layers, do you consider the like resonance in each layer, and then you strategize your design and optimization based on that? For example, if you know that I design based on the material property, I have a quarter wavelength standing wave in this layer, then I can absorb a lot of sound, a lot of energy there. And subsequently, I design my layers based on the thickness and the wavelength. So do you follow that strategy when you are designing that, to get a rough idea about like how much my thickness should be and how many layers I can fit for this space, this thickness?
Yes, good point. Yes, I understand your question. Should we follow the strategy of quarter wavelength, thickness, or the position? But if we conduct the optimization in MATLAB, we really need to figure out the most compromise or most cost efficient strategy. I tried from, I think it's more related to thickness or the position from the rigid back for the quarter wavelength resonance, and I tried different thickness, and I tried from 1 layer to 8 layers. Actually, on the end, I didn't see so much difference, so I changed the strategy to get the either thinner structure or the less weight material. So I think I presented on acoustic Sydney for the even 7 or 8 layers. There's no big difference for the final result. But
Okay.
the main point is still the overall thickness.
So do you think it's this type of difficulty in predicting just using the thickness and the wavelength is because of the porosity of the material?
I don't think the porosity affect too much for in some cases, but still the thickness is more important. The porosity is more related to, as I mentioned, for the surface area or the micro structure, for example, the pore collections, and then how the sound waves get into, so how the sound get dissipated because of the viscous thermal effects.
Yeah.
I think it's good point because we can't use a simple material to generate very excellent sound option with a very low thickness. I guess the final idea of the solution is to use such kind of combination, to use metal material combined with the porous material, because for metal material they are very good on low frequency range. If I can go further, for example, to do optimization for modular for multiple different types of material, I think definitely it will be very great or very interesting to see the results.
So what I understand, it's mostly the absorption is due to thermal viscous loss rather than like trapping the energy in a waveguide in this type of material.
I think both.
Yeah. Okay. And I have another question, which is not exactly related. So is this JCL model can be used for water as a medium instead of
what water? Well,
yeah. So let's say someone wants to do this for underwater acoustics and they want to build a noise sound absorber in underwater application. Can we use JCL?
I think so. I think so because you need to change the saturated fluid from air to water, but then of course you need to figure out the characteristics of the fluid, either air or water or something else.
Okay, thanks. That's all from. Thank you.
But sorry, one thing I need to mention, the JCAL model or JCAL model, they are in the category of semi-phenomenological model. So in this model categories, the porous material was assumed as rigid frame. So if you have the material with an elastic frame, the semi-phenomenological model is no longer feasible or suitable. So you may need to try the build model.
Okay. Thanks.
You're welcome.
Do we have more questions? I'm wondering what sort of optimization algorithm did you use in your simulations?
Sorry?
What sort of optimization algorithm did you use?
Okay. I tried one particle algorithm, generative algorithm, and the NetMed simplex algorithm. On end, I found all of them have the similar result, almost the same result, but maybe generative algorithm takes short time. For example, for me, wait, it takes me, because I made a for loop in my lab to get the result for this graph. It takes me 10 to 20 minutes to run the operation in one for loop. So it's quite, I can say, only for the calculation takes a really long time. But I think I may also try, because currently I get familiar with the ladder mat simplex algorithm. So I'm still using that one. Maybe I can switch to generative algorithm. It may save some time, but I didn't try it for this one. So I may need to try it.
If there are no other questions from the audience, maybe we thank the speaker for his wonderful presentation. And it seems like a very interesting topic. So I'm very eager to see what comes after this. And maybe we talk after this again for how we can collaborate. Right?
Yeah, for sure.
Yeah.
Yeah.
Thank you again, Tao. And
you're welcome. Thanks a lot for your invitation.
Yeah. Thanks again for the audience as well for their participation. And
Thanks.
Thank you. It's an interesting presentation.
Yeah, thank you.
Thank you, everyone. Bye.
Okay. See you. Bye-bye.